All right, recording is rolling. Welcome to Monday, September 18th. The exciting week I got lined up for you guys. So, right, main thing we're doing today is this page. I gave you guys this page about a week back, so gonna do as many problems as I can here. More clear with you guys on that. Right, some other stuff going on. Let me go bottom to top. How about that? Right, don't worry about any class here. I'm messing with you guys. These puzzles that we're going to do today, they aren't due for like almost 2 weeks, right? But I like to get you guys materials like plenty ahead of time so that as we're doing the labs in class or like demos, you guys can like read along. That okay, kind of see what questions are coming up and how that might align with like the spring scales lab or something like that. Right? Projectile quizzes, yeah. So those were due back on Friday. If you turn it in back on Friday when it was due, then I graded it over the weekend. Most of you guys did really awesome on that. Usually projectile motion is like some of the hardest stuff for students. So that's if you thought that was not too bad, then I think the rest of the year is going to look pretty good, right? I'm still waiting on a few to come in. There were some students absent, blah, 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 right? I was going to make a top scientist list, but oops, a little bit late on that, but maybe tomorrow I'll have a top scientist list for you guys, right? All right. Also, some technical details, just some phrases I hear students using, blah, 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 right? Point up some stuff. So one has to do with graphical relationships. Right? Like a really common graphical relationship in this class is a parabolic type relationship. For example, one of the very classic ones is when you guys were rolling these Hot Wheels cars down inclines. Some of you guys were saying, look, what's the relationship between how far it goes as a function of how much time it's been rolling for? And that was one of these type relationships. It was like x is proportional to time squared. So if it was rolling for 3 times the amount of time, guys, what's a factor of 3 squared? Be 9, right? It would be like 9 times the distance. Ooh, 3 times the time, like 9 times the distance. That's what, right? Uh, a lot of times I'll ask students, what type relationship is that? And very often I hear students say, oh, exponential. Okay, because there is an exponent, so it might be logical to say something like that. Right? If you open up a math textbook, when they talk about exponential curves, that's actually a completely different class of curve. That's something totally different, right? Uh, so when you say exponential, you're talking about the base of some number, and the independent variable itself is in the exponent. Now, we hardly ever see that in this class, right? Like almost never or never. Like I don't think any of the labs exponential relationships ever show up, right? Lots and lots of parabolas, but like almost none of these. Where do you actually see exponential relationships in real life? Give you guys some examples, like interest rates, right? So if you have money in the bank, it's accumulating interest. That's one of these exponential curves. Inflation works like this. Moore's law. Do you guys know Moore's law? Like the number of transistors you can fit on a computer chip economically like doubles periodically. So like that's like one of these two, right? It's like sometimes you hear the term logarithmic. It's like the inverse of this. Right? Again, these are totally different classifications of curves. Let me give you guys a numerical example. Suppose x was like 300. You square that. Okay, so 300 squared. Ooh, 90,000. That's a nice big number, right? 90,000 compared to 300. That's pretty big, right? But what if you just reversed those two and actually made it exponential? Because what is 2 to the power of 300? Instead of 300 squared, what if you do 2 to the 300? Is that very different? Is that going to be very different? Because 2 to the 300 is like the number of atoms in the observable universe. You guys see how exponential blows up really fast compared to like parabolas? Right? Is that so? Right, little detail there. Another little detail, and this is mostly for my AP kids, is terminology type stuff. Right? What is a gravitational force? Like this 1 kilogram, this is 1 kilogram of mass. I feel a downward force on it. Like about 10 newtons. That's like 10 newtons of weight. I'll call it weight, or sometimes force due to gravity. And I might write it either way, like mass times gravity field or F sub g, or force due to gravity. Right? Our students, what is the downward force? A lot of students say, oh, gravity, which that's fine for me. I'm not gonna, I don't really care. But maybe someday you guys are taking a college class, or maybe even AP one day, right? One or the other. So that is something like an AP grader would count against. Yeah, that's most of my AP graders or my AP classes. I'm telling them, don't say gravity, say like force due to gravity or weight. It's a weird little technical thing. But anyway, that aside, right, let's get as many of these done as we can. And the last class I was able to do, well, here, we'll just go as far as we can here, right? And so number 58, 58. You toss the ball straight up in the air. Draw a free body diagram for the ball at 3 points during its motion. On the way up, at the very top, and coming back down. Identify those forces acting on the ball and their agents. Okay, so there's a part B and a part C. So let's do part A first. And we'll worry about those other parts. So number 58. 8. Right? Now I can throw a ball straight up, goes straight back down. Right? I'm gonna give it a little bit of a sideways motion. Right? Or maybe if you like, maybe the sideways part is actually a time axis. Is if I put a time axis right here, right? It's like tick tock, but maybe the ball's just going straight up and straight down, right? However you think of it. At some point, it's headed on the way up, so it has an upward velocity. Say like velocity that way. At some point, it's at the very top, right? And at some point, it's coming on back down. So give it like a downward velocity, right? Something like that. Would that be true? Right. Now, you guys remember free body diagrams? We took 2 days last week. I think it was Thursday, Friday, to go through a whole PowerPoint of like many different free body diagrams. Right? And guys, what type of vector do you draw on free body diagrams? Do you care about velocity vectors? Not so much. You care about what kind of vector? Forces, right? And then in December we might get like torques also, but we care about forces, right? Now, I'll give you velocity vectors maybe off to the side sometimes for context, because the context might be important. But for free body diagrams, I really care about drawing force vectors, right? So let's draw some force vectors. How about, does the ball at each of those positions have a weight acting on it? Right? Yeah. So and the weight points which way? Straight down. Right. So we got weight, right? And it's the same at all 3 positions, isn't it? Right? So I'll call it mg because that's what I've been calling it all along this class, right? Mass times gravity field. If you want to do F sub g, force due to gravity, you can do that too. Right? One way or the other. Okay. Right. In fact, if the ball's in a vacuum or approximately a vacuum, couldn't that just answer the entire question for part A? This is part A, right? Part A, right? And then you'd be done, right? But we also did start to consider last week air drag. What if you want to make it a little bit more complicated? Consider air drag. Let's do that. Let's throw air drag in the mix. Right? So how does that change this one on the left where the ball's like headed upwards? How does the air drag? Yeah, you guys are saying point down, right? So let's do a little side motion there and say down, call it F drag, right? Because you guys remember drag always points opposite of the motion, right? If the ball's headed straight up, then the air drag's pushing straight down. Right? How about at the very top? What's the air drag at the very top? 0. Yeah. You guys remember that drag force is proportional to the speed squared? It's something like 1/2 coefficient of drag, density of the air, cross-sectional area that's pushing against the air times the speed squared, right? But here's the boiled down version that you guys care about. As if you throw an object straight up in the air, at the very top it has 0 speed, therefore 0 air drag. Right? So the free body diagram of just its weight, that's it. So we're already done. Right? Then the ball's headed straight back down, straight back down. Now the air drag points which way? Upward. Right? I'll also do F drag this way. Right? It's good. So opposite motion. It's moving down, so the drag force is up. Right? In fact, as it falls faster, I bet that drag force is going to be larger. Right? Sure. Right. Part B. What is the velocity of the ball at the very top? So part B, velocity at the top is how much? 0 meters per second, right? I knew it drew like a parabola shape, but you guys remember it's just the time axis is taken to the right way. This ball is only going straight up and down, right? And part C, what is the acceleration of the ball at the very top? What do you guys think there? What's the acceleration at the very top? Yeah, g downward. Right. Or if you like, you could say about 10 meters per second squared down. Be like the same thing, ground earth, right? For sure. Right. And you can get that. Here, the old way of doing it is you just kind of either to be a fact that free fall gravity was the same everywhere, or you could go out and measure. Right? You could drop some height and break out a stopwatch, and you could do a kinematic calculation. Something to do with these 3 amigos right here. Right. The new way of doing it is we're going to say it's the net force acting on the mass, which is Newton's second law of motion. Right? You guys remember Newton's second law of motion? That's what that would be. So the net force would be its weight at the very top, acting on its mass. Oh, look, it's the same thing. It's still g. and then the direction is downward. We're still talking about vector quantity, so the direction matters. Okay, you guys good there? All right, all good, all good. Number 69, assume a scale is in an elevator on Earth. Scale is in an elevator on Earth. Okay. What force would be on the scale for a 53 kilogram person in these following situations? They give us 5 different situations. Ooh. Elevator moves up at a constant speed, slows at 2 meters per second squared while moving upward, speeds up 2 meters per second squared while moving downward, moves downward at a constant speed, or slows to a stop while moving downward. Ooh, okay. So let's get see 69. Okay. Oh. Part A, moves up at constant velocity. Moves up at constant velocity. Okay. So if I got a elevator here, here's a guy standing on a scale, maybe some version of that. Okay. Inside the elevator. Okay. And I've got upward at a constant speed, right? Constant speed, constant velocity. Right? So see what forces are acting on this guy. Let's do free body diagram. Right? Does this guy have a weight? It's pulling straight down? Yeah, it's got a weight. Earth's gravity field's pulling straight down. Right? There's also a normal force reading from that scale, isn't there? Normal force reading from the scale. Right? Now, guys, if he's moving at constant velocity, and he's standing inside the elevator, how does that feel compared to the elevator being at rest? The same? The same? Exactly. Hey guys, if you were in an elevator moving upward at constant velocity, could you distinguish that from being at rest? No. What if you're moving down at constant velocity? Would that feel exactly the same as moving up at constant velocity? Yeah. What if you were moving really fast upwards, but it was still constant velocity? Could you tell how fast the elevator is moving? No. Right? You don't know. Right? So the normal force rating from the scale, and that would be a normal force, right? Or normal force from the scale. This is going to balance out. Just wait. See how those are same magnitude? You see that? Same magnitude? Right. All right. So what was the question? What force does the scale read in each of these contexts, right? So for constant velocity, I'm going to say acceleration is 0 meters per second squared. Therefore, the net force is equal to 0 newtons, right? It says the sum of forces. That's the net force, right? This is sum of forces, which is the net force. Same idea. Okay, so 0. Okay, which means that the normal force up minus the weight down is equal to 0, which means that the normal force is equal to the weight in terms of magnitude. Right? Maybe I did a little bit of overkill there, but here, I guess that proves that's equal to that. Right. Okay. Let's pop in some numbers. So the normal force reading on the scale, this guy 53 kilograms, and a gravity field of 10 meters per second squared. So that can be like 530 newtons, right? So if this guy's just standing out on a sidewalk, steps on that scale, it says 530 newtons. If he's moving upward at a constant velocity, that scale still reads 530 newtons. If he's moving downward at a constant velocity, that scale still reads 530 newtons. Right? Guys got that? Actually, that was one of the other questions. Part D says he moves downward at constant speed. Guys, moving downward at constant speed, isn't it exactly the same thing? So this is part A, but this is also part D. Right? That's A and D. Right? Those are, like, if you're staying inside the elevator, they'd be physically indistinguishable. Okay? Moving up at constant velocity, moving down at constant velocity. So, same thing. Okay. All right. Part B, slows while moving upward. Slows while moving upward. What's up? Part B. Slows while moving upward. Right? Wonder what this free body diagram is going to look like. Got a guy standing on a scale. Right? Well, I bet his weight is the same as whatever, right? So his weight doesn't change. mg, right? It's got some mass, same gravity field, and it's different. Okay? Right. Now, guys, moving up but slowing to a stop. Are you going to feel kind of light or kind of heavy? What do you guys think? How do you guys think moving up but slowing to a stop? How do you guys think it's like partial free fall? You might feel kind of light. Feel kind of light. Yeah, that's what I'm thinking too. Right? I think the free body diagram is going to look like this, where it's a very small normal force compared to a large gravitational force. Right? So I can say the magnitude of the weight is greater than the magnitude of the normal force. Okay? This could actually be one of two different situations, this free body diagram. Right? FBD, free body diagram. Okay? This might be either moving up and slowing, right? Or moving down and speeding up, like speeding faster. Okay. Moving up, coming to a stop, or you go down faster. That free body diagram applies to both of those. In both cases, you're going to feel kind of light, right? In fact, if you take this to an extreme, could you just take this normal force all the way to 0? Or maybe the tension in the elevator cable, just like cut the cable. Both of those could be like you move up, like if you toss the ball straight up, it's going to slow, right? Or if you drop a ball off a cliff, it's going to speed up, right? That would be like pure free fall, right? So what's the scale reading? What's that normal force reading? Well, now we're going to need to break out Newton's second law of motion. Guys, remember the net force is equal to mass times acceleration. And the net force in this case is going to be, here, I'm going to call it down the positive direction. So I can take the large force vector and subtract the small force vector, right? And that'd be mass times acceleration. But this acceleration would be in the downward direction because it would be accelerating downward, right? Guess that? Okay. And the question here is, what is the normal force reading on that scale, right? Okay. I'm going to go ahead okay. I guess there's a couple ways you can handle this. You could plug in numbers at this point, or you could solve in terms of variables. Maybe I'll do both with you guys. How about that? Let me split my page here. I'll do one of each way. So let's do in terms of variables and with numbers, because they're going to lead to the same answer, right? In terms of variables, I can just do the algebra straight with what I got right in front of me. Get the normal force reading on the scale is mg minus ma, right? Oh, same mass. I can factor that mass out, g minus a, right? So there's a general solution, right? And then I can plug in numbers at that point if I want to, right? If I plug in the numbers right away, then that's going to be like 53 kilograms times 10 meters per second squared minus the normal force results in 53 kilograms accelerating down at, I think it said 2 meters per second squared, right? That's what it results in, something like that, right? Okay. So I got 530 newtons minus the normal force reading on the scale results in 106 newtons. Okay. I do a double swap right here. Let's do 530 minus 106. So algebra switch around. The normal force reading on the scale is 424 newtons. Okay, so there's the numerical answer. Okay. Let's check my general solution. If you plug in 53 kilogram guy at 10 meters per second squared, but minus the 2 meters per second squared, right? Because it's going to feel a little bit on the light side. Okay. What's 53 times 8? 10 minus 2 is 8. Oh, it's the same thing. It's 424 newtons. Okay. Okay. So solve in terms of variables, plug in the numbers at the end. Okay. Now I have a general solution, and then just plug in the specific values. I get that. Right? Or you can plug in the numbers from the get-go and then done all the algebra after the fact. You still get the same thing. Okay. Okay. You guys go there. Okay. Part C says speeds up 2 meters per second squared while moving downward. See, part B was slowing down, moving upward. Part C is speeding up, moving downward. Guys, is that physically identical to what we just did? It is. It is. Right? if you're moving up slowing, or if you're moving down speeding, right? That's, oh, I actually listed that out right here. B and C are physically identical to each other. So B and C are the same thing. They got the exact same answers, right? If you were inside an elevator and stepped on a scale and you were like really light, you're like, oh, I know I weigh more than that, right? The scales show me light. I feel really light, right? You might be doing either one of these, but it would be impossible to know which one you were doing. Okay. Here's the okay. There's one more. It says slows to a stop moving downward. Right now, this one we haven't quite done yet. Right, we haven't done this scenario yet. 69 part E. Okay. Slowing to a stop while moving downward. This guy in the elevator on a scale. Okay. The center mass stop. Okay. So now he's got some weight pulling down. There's mg. Okay. You guys, if you're moving down and slowing to a stop, which way overall are you accelerating? Opposite of the motion, which would be up, right? Kind of like a car braking to a stop. It's moving forward, but it's accelerating backward. Yeah, same thing here. There's a huge normal force reading from that scale, right? A huge normal force reading compared to, well, Earth's gravity pull doesn't actually change, right? So this is larger than this. So we have the normal force reading, the magnitude is greater than the magnitude of the weight, right? Which could be either moving down and slowing to a stop, or moving up, speeding up. So moving up faster, 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 right? Okay. So if you're inside the elevator and you feel really heavy, it might be either one of those scenarios, but it would be impossible to know which, just being inside the elevator. Okay. Right. So let's break out Newton's second law of motion. Net force is equal to mass times acceleration. In this case, here I'll call up positive this time. So do the normal force reading up minus his weight down results in mass times acceleration. Okay. The question, just like last time, was what is the force rating on the scale? That's the normal force. Okay. I'm going to do the same thing I did before too. I'm going to split my paper and do it 2 different ways. Variables and with numbers. Okay. So in terms of variables, the normal force would be, add that over, that's mg plus ma. If you like, you can factor out the mass and do g plus a. Right, now I have a general solution. You can plug in any mass, any planet gravity, any acceleration of the elevator, you get the rating on the scale. Okay. If you want to plug in the numbers first, whoops, so it's minus right there. Right. We got a 53 kilogram guy accelerating, no, we'll start with Earth gravity. Just run out of ink. It's pretty close to the end of the line for that guy. Meters per second squared is equal to 53 kilograms times 2 meters per second squared. Okay. Now the normal force minus 530 newtons is equal to 106 newtons. So now I'm going to add that over. It's 530 plus 106. I'm looking at 636 newtons. Woo! Now this guy feels really heavy. Because out on the sidewalk, he said, oh, I weigh 530 newtons. Now he's in this elevator that's accelerating upward. So it's like over 600 newtons. Right? Oh, let's make sure my general expression would have worked out. 53 kilograms times like that, right? Okay. I hope this is the same thing. It better be. What's 53 times 12? Oh, it's the same thing. 636 newtons. Okay, same thing. Okay, you guys got that? All right, are we good with the elevator? Okay, so 2 last things with the elevator. I'm gonna switch my screen over here so we can watch this demo. Not screen 3, it's gonna be. All right. Okay. I'm so sorry, guys. My computer's being really laggy. What happened? Okay. We're going to see this elevator. Hey. Okay. Ooh. Yeah. You guys saw the needle jumping around? Let's get one more shot of that. Let's try again. So it looks like this guy weighs, I guess, 200 pounds. It probably is 200 pounds. Right. In the elevator, bam, woo, that needle just jumped up, right? Which means he's accelerating which way? Upward, right? Now, since he started from rest, you know, the elevator must also be moving upward. But if you didn't know that, you just saw this context, then you definitely know it's accelerating upward, right? And then the needle jumps all the way down to like 180, right, which is less than its usual weight. So in that case, the elevator is actually accelerating which way? Like down, right? All right, so you guys got that? Right. And the last thing I want to do with the elevator is show you guys that, hey, there's a poster. It's like Neapolitan ice cream. It's the same one hanging over that door right there. You see over the door right there? Right. Oh, this is why I just arrived with you guys. You got elevator. The elevator might be in equilibrium, accelerating down, accelerating up. Okay. The only difference between what we just did in the notes and this poster is I'm calling this tension force, like the tension in the cable that's holding the elevator up, versus in the notes I did the normal force, like the guy standing on the scale. But otherwise, it's the same thing. Oh, look, here's the answers right down here. So let's start with the middle. Elevator in equilibrium. That might be the elevator could be at rest. Could be, right? But it didn't have to. All right, right. The other possibility is that the elevator is moving at constant velocity. Right? And it might be up at constant velocity, might be down at constant velocity. But it's all leads to the same outcome. The elevator's equilibrium anyway. So the tension in the cable or the normal force rating from the scale, if you like that, right, it's just equivalent to the weight, right? Equilibrium. Right? Now, if you're accelerating downward, that it could be, again, like one of two things might be going on. You might be moving down faster, 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 or you might be moving upward but slowing to a stop. Both of those are downward acceleration, and they both have a free body diagram that looks like this. I just derived this for you guys. Right? And well, kind of a shortcut way to think of it is to take mass times, you know, the difference in acceleration values, then you'd be a little bit light, right? And the opposite situation is accelerating upward, which might be moving up faster, 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 but it could also be moving down, slowing to a stop. That's what we just did, right? And I derived this for you guys. Oh, hey, look at that. It's like mass times acceleration, but you're like adding together to acceleration values, right? Kind of the shortcut way to think of it. Okay. You guys get that? Right? Elevator physics. Oh, yeah. Elevators are fun. Right, number 73. A 65 kilogram diver jumps off a 10-meter tall tower. Find the diver's velocity when he hits the water. And then, okay, there's a follow-up question, right? But actually, this first question, I think that's actually last unit, right? Isn't that kinematic motion? Like if you know the height of the tower, you want to know how fast he's hitting. That sounds like kinematic motion. Do you guys think that has anything to do with the fact that he's 65 kilograms? It's like he could be like 35 kilograms or 100 and something kilograms. You get the same answer for part A, right? That's the Galileo experiment. You guys remember Galileo was dropping different stuff off the Leaning Tower? Like, let's see, like this guy versus this guy. They fell side by side, crashed at the same speed. So let's go back to kinematic motion for part A, number 73A. Let's have a little tax BV table. You guys remember time, acceleration, displacement, initial velocity, final velocity. Right, I get you guys a picture. How about that? Right, this guy's standing up here. Got a use this right here. There we go. H equals 10 meters. Okay, it's gonna splash. Okay. So I know this is 10 meters. I think it's safe to assume he starts from rest, 0 meters per second. Oh, and we also know Earth's gravity field, 10 meters per second squared. Okay, that's 3 kinematic values right there, isn't it? Okay, let's get this. Okay. And the question is, how fast is he crash landing in the water? Right? Sure. That sounds like a job for the 3 amigos, or at least one of them. So if you're trying to figure out crash speed based on drop height, which one of those expressions leads you directly to the answer? First, second, or third? Okay. there's actually a couple ways you could do this, right? Let me show you guys the hard way and then the quick way. Right? So the hard way you could do is say, well, I know the height of the cliff, so I could solve for the fall time. It would boil down to the college equation. Okay, like you guys remember reaction time with the ruler? You could do that. Then you could get that fall time and plug it into the second equation, and you can get the crash speed. Okay? But you could just jump straight to the third one, and the third one will tell you crash speed is a function of the height of the cliff. And okay, guess that this sort of it takes care of it. So let's do it. Let's do that. So I'm going to go final velocity squared, which we're solving for, is equal to initial velocity squared plus 2ax. Just like that, right? Okay. This just goes to 0. Anyway, whatever. Okay. So the crash speed is going to be the square root of 2ax. Or if you like, you could have said 2gh. Right? Is that right? Gravity's type of acceleration. The height of the cliff is the displacement. Okay. So let's pop in some values. I'm going to go square root of 2 times 10 meters per second squared. Height of 10 meters. Square root that whole deal right there. Okay. You see how my square root is extended? The square root bar is extended over that entire inside expression, right? In the past, I've seen a lot of students that like want to stop the square root bar halfway and then it's confused. Well, what's being square rooted? Like the whole inside expression is being square rooted, right? So let's see, let's the square root of 200. Looking at that crash speed is 14.14 meters per second. Truth be told, it's probably too many digits of precision, but since this is like a middle step to answer the second question, I'll keep some extra digits that I can't truly know, just to save my rounding for the very end, right? Okay. So you guys get that? Okay. He's crashing about 14 meters per second. That's probably as best I could say. It's about 14 meters per second. Okay. All right, you guys ready for part B? Part B says the diver comes to a stop 2 meters below the surface. Find the net force exerted on him to come to a stop. Okay. So 73, part B. Okay. Now he's hit the water, a splash, and he's going to come to a stop like 2 meters down. Plus height change is equal to 2 meters. I'll just say 2 meters. Did they say 2.0? Yeah, they gave you 2 digits. They said 2.0 meters. Right? Right. So let's see, he's crash landing right about there, and he goes like 2 meters down and comes to a stop. Okay, stop. Okay. I think it's going to be a 2-part question because there is kinematic motion going on here. Like I know here, I know his initial velocity right here is 14.14 meters per second. I know his final velocity is going to be 0 meters per second. And I know the height change. That sounds a lot like what we just did, right? Except here we're solving for the acceleration. And then we're going to take that acceleration and switch over to dynamics and Newton's second law of motion to figure out the net force. Ah, you see that? Right. So I need another tax VV table. Okay. Kind of like what we just did, except this time I want to know what rate is he slowing down? Looks like he's slowing down in a hurry. I see he's slowing down in a hurry right here. Okay, switch my. Yeah, okay, go. All right. We know this all. Okay, we know he's crash landing at like 14 meters per second. He's going to slow to a stop 0 meters per second, and this all happens in like 2 meters. Bam, bam, bam. Right. You guys see it's going to be the same kinematic expression that we just used before. Right. We're still using the this third amigo right here. Except this time we know everything except for the acceleration, but we're solving for the acceleration. Like what rate is he slowing down after he crash lands in this water? Right. Right. And then once we get that, here I'm going to write a word above this variable acceleration. I'll call this a bridge. A bridge. It's a bridge between kinematic motion and dynamics. Because the old way of thinking about acceleration, which we're actually focused on right now, is it's a rate change of velocity. The new way of thinking about acceleration has something to do with the net force acting on some mass, which is Newton's second law of motion, right? So that's the variable that's going to connect kinematic motion to what forces cause this motion. Okay? All right, so let's go final velocity squared equals initial velocity squared plus 2ax. Right? solving for the acceleration. And then we're going to 0 from 14.14. Here's a second, square that. I could get a negative acceleration, or I could just say minus, however I want to do it. Okay, but this all happens over 2 meters. 2 meters. They said 2.0 meters. Maybe I should just say 2.0 meters. 2 meters. Right. Okay. So a couple algebra steps later, I'm going to say the acceleration then is going to be 14.14 meters per second being squared, all divided by 2 times 2.0 meters. Right. Just did some algebra right there. Out over divide. Right. What's 14.14 squared divided by 4? I'm looking at 50 meters per second squared. 50 meters per second squared. Right? Oh, even that isn't the final answer, but it's a really important middle step because we just found the bridge between kinematic motion and what the actual question was something to do with net force. Okay, right. But I want to pause here anyway because, guys, 50 meters per second squared. Have we talked about like a G force or how many G's? Have we talked about that yet? How many G's? Right. Guys, how many Earth gravities are we in right now? 1. We're in one Earth gravity, right? If you're out in space floating around, how many Earth G's is that? 0, right? But suppose you're in a car accelerating forward, you feel a little bit heavy, right? Or maybe you're in like a theme park ride or on a roller coaster, you feel kind of like heavy and light. You might be like, ooh, like 2 G's, 3 G's, right? Like 3 times your weight, kind of, right? Okay. But G's is kind of an acceleration concept. How many G's is this right here? Like as he's slowing down the water, he's going to feel really heavy. How many times heavier compared to normal? How many G's is that? Let's see, every 10 meters per second squared is a G. It's like 1 G. Hey, isn't this like a multiple of 5? 5 G's? Okay. Did I show you guys that guy in the centrifuge? I don't think I did. Hey, here, I'm going to switch my screen over. Some of my classes, we had like an extra minute last week. So let me dig up that video. Share this here. Oh man, Slaggy McLagster. Come on, play this video. All right, so you guys are about to see. I think this guy's like a fighter pilot training. Right? You guys see G equals 1. He's in a centrifuge, and they're just about to start in the centrifuge. Here we go. Keep an eye on the G counter. Spin him up. Ooh, look, he's getting up to 9 G's. I see that? 9 G's. Now, that's about the maximum the human body can take. Not sustained. Right? Like if they left him there all day, then it's okay. That's the ride of his life. But yeah, they only left him there for 2 seconds. Yeah, so he's doing all right. Yeah, you only put him in 9 G's for a few seconds. Yeah, he all right. He all right. Right. Ooh, and this guy can splash in. Ooh, he's like about half of that. He's like 5 G's. Right. So we still got one more thing to do. Actually, I got some space over here. Maybe I should just finish this right here. Because Newton's second law of motion. You guys remember net force equals mass times acceleration? That's Newton's second law of motion, right? And we're finding what is the net force. We know the sky is, did it say 53 kilograms? Is that what it said? No, 65, that's what it was. Right. 65 kilograms, 65 kg. And we know he's slowing down. Guys, this is an upward acceleration. Maybe I should give a direction because this is a vector, right? He's accelerating at 50 meters per second squared. Wouldn't that be true? Right. So let's put that all together. 65 times 50. Okay. This is 3,000 and something newtons of force. Or if you like, you could call it like 3.2 kilonewtons. Do something like that. Would that be true? Right. Okay. Now, one last detail I want to mention about this is really the net force. Right? There are multiple forces on this guy as he's breaking to a stop in a hurry. Okay? So suppose I do a free body diagram on this guy. Well, he's breaking to a stop. Okay. Maybe like right here. Okay. So I'm thinking this guy has a weight mg, right? I mean, Earth's gravity is still pulling down on it, gravitational force, okay? But there's also a huge drag force, F drag, and there might even be like an additional F sub B buoyant force acting on the guy, right? But if you take the difference in all those forces, there definitely is a net force on them. There's a net force of 3,000 newtons. Okay, you guys get that? All right. All right, 74. Car racing. Hold on. Did we miss something? No. 74. Car racing. A race car has a mass of 710 kilograms. Starts from rest and travels 40 meters in 3 seconds. The car, uniformly accelerated. What is the net force exerted on the car? Net force exerted on the car. 74. Oh, sorry here. Okay, so we got mass is 710 kilograms. And okay, it starts from rest and goes so far in so much time. Doesn't that sound kinematic? You guys think it's kinematic? Okay, so kind of what we just did with the guy diving in the water. So, well, he's slowing down at some rate. We can use kinematic motion to figure out the rate he's slowing down. We're going to take that acceleration, plug it into Newton's second law of motion. Same thing with this car. See a free body diagram of this car. I bet this car has a weight. I bet it has a normal force. If it's a flat road, then it's okay, right? This car is probably trying to move to the right, might be, right? And then there would also be a, I'll say the force from the road, right? Oops, road, right? There's a force between the tires and the road to allow the car to speed up, right? Like if this car was sitting on an air hockey table or like an icy patch, it'd probably be really hard to spin out of there, right? So you need some traction, right? So let's do kind of what we just did. Set up a tax VV table here. Right? We know the car starting from S, bam, 0 meters per second starts. Right? It took 3 seconds to go 40 meters, so in 3 seconds went 40 meters. Right? So we're going to find the rate that the car was speeding up. And once we got that, we can kick over to Newton's second law of motion and figure out what is the net force in this car. The net force would be the actually, this would be a friction force, is what that is. I'm thinking of it. The force from the road is that would be a friction force. Right? So, which of these guys? First, second, and third? Read. Yeah, I like the first one too. Okay. The reason I like the first one, see, we don't know how fast the car is going, although we could figure it out. Okay. But we do know how far and how much time. Yeah, that sounds like a job for the first one. Here's how far and how much time. If you start with the second one, you got 2 unknowns. You don't know this and you don't know this, so you're kind of running into a dead end. But I think the first one's gonna take care of that for us. So let's go. How far it goes is v naught t plus 1/2 at squared. Now the v naught t just goes away anyway. It goes to 0. Okay. So we got 40 meters he went. We're trying to figure out the rate he's speeding up. He does this all in 3 seconds, and then square root of 3 seconds. 3 squared is 9. If this was some algebra, right? So the acceleration is what is 40 times 2 divided by 9. I'm looking at 8.89 meters per second squared. Okay. Now that's not quite the answer yet, but it's a really important middle step. Okay. So we use kinematic motion to figure out the rate that he's speeding up. Now we're going to take that and go over to Newton's second law of motion. You guys heard that? Okay. So the friction force between the tires and the road that was allowing that is the net force, mass times acceleration. The mass of the car was 710 kilograms. And the acceleration of the car, 8.89 meters per second squared. See, put this all together. So it looks like 6,311 newtons. Say 6,300 newtons. Right? Say 6.3 kilonewtons. Right? you know, 2 digits of precision on those numbers. Maybe that's about as much as you could know. Okay. All right. You guys good there? All right. That was a good pause point today.